Okay, hello and welcome everyone. My name is Peter Robinson, and today I've got Diego here who's going to tell us a new way of doing things. It's an alternative to Ethereum, but should be interesting to get a different perspective on what blockchain is and can be. So over to you, Diego.
Hi. Hello. My name is Diego Nahab, and I'm with the Machine Reference Unit at Cartesi. And I thought it would be interesting to show you some of our work in making an entire Linux stack work as if it was a smart contract. So for those familiar with the jargon, let me give you a context for this talk. Our project centers around a scalability solution for Ethereum-based blockchains. So it's not an alternative to Ethereum. It's a way to add scalability to Ethereum, right? So this takes the form as an optimistic rollup, and the correct behavior is enforced by a fraud-proof mechanism. But each application runs on its own chain, right? So that's where most of the scalability comes from. So what sets us apart is that our fraud-proof mechanism allows a single honest civilian to defeat an entire army of cheating Sybils. And another difference is that our applications run on Linux. So the talk will focus on getting the Linux side of things going. If you're interested in our dispute resolution algorithm, let me know, and I can arrange for a colleague to talk about it at a later time. I'll describe a simpler dispute method just to illustrate the requirements that disputes impose on our stack. So unfolding this to those unfamiliar with the jargon, here's what an optimistic rollup might look like, right? So everybody must first agree on a state transition function and an initial state. So this is like Ethereum and the Genesis, for example, state. Right? Now, everybody must agree on a sequence of available inputs. And in a sense, these are all known to the base layer, right? That you want to add scalability to. So when you feed the state and an input to the transition function, it spits out an updated state and a bunch of outputs. So you can fold the state, the inputs, and outputs into a capital letter M, and everybody then can run this transition function off chain. Nobody disagrees, say, on the nth transition up to the nth transition, then the outputs up to then can be trusted by base layer. If somebody disagrees, then can engage with base layer to start a dispute over these results. But the premise is that if you set the incentives right, nobody will dispute because whoever is cheating will lose. And you almost never need to involve the base layer on the transition function itself. This is all very nice and abstract, but let's get more specific, right? So imagine you're implementing a decentralized exchange. Now, the state would include current balances of all traders in all supported tokens. It would also include the outstanding orders in the order books for each supported token pair that you can trade, right? And an input would include, say, a bunch of deposits, new trade orders, and perhaps withdrawal requests. The outputs would be what we call vouchers, and a voucher would allow a withdrawal to be performed in base layer to move funds from the exchange wallet to the trader's wallet. This, of course, would only be allowed once everybody agreed that a given state has been settled. Now, this function F is actually a computer program, like a real computer program, and implements the state transition function for the exchange. And our goal is to let users implement this program pretty much however they like. So here's a general idea of how disputes work. Assume two parties disagree somewhere in a sequence of straight transitions between A and B. We want to find the first transition where they disagree. So we ask them through base layer if they disagree before the midpoint transition. And with the answer, we can have this interval of disagreement, and we can then go on with this binary search, if you will, until we reach a single straight transition. Now, only the honest party will be able to prove their opinion about the state transition. Remember, the state transition function is just software, and its state is just data. but the function can be too expensive to run directly on base layer, and the data can be too vast to actually submit to base layer. So we want to transplant the transition function and its state to a special emulator that can continue disputes still off-chain. But the thing is that no man is an island, and neither is any software. So your code usually depends on the code of others, and it depends on your choice of programming language, the programming languages used by the software components you want to use. And these components and programming languages depend on an underlying operating system very frequently. So finally, the operating system itself depends on certain features being supported by the underlying computer architecture. So trying to extricate existing code from its dependency graph is often a futile exercise in frustration, right? The alternative would be to reinvent the wheel and code everything yourself, many wheels, in fact. And if we want developers to adopt a technology, we shouldn't force them to go through this hell, right? We should just be accommodating. Now, you could argue that if you give developers power, they will abuse it, right? But I don't want to be in the business of telling people how to do their work. I want to empower them to do their work however they like and to be as productive as possible. So let's look a little bit in more detail at how to make this happen. So I'll borrow nomenclature from the C and C++ standards. And there are two parts of these standards. The first part deals with the fact that processors run code at a very low level of abstraction that disregards human concerns. So the freestanding part is a small subset of the standard that simply offers higher level constructs for humans. So stuff like literals, expressions, conditionals, basic types, function classes, statements. So they just isolate the programmer from details of the given processor. So you can change the compiler backend to target any architecture you like, right? Now, the hosted part of the standard is a lot more ambitious. This aims to simplify many of the common tasks that a programmer would want to perform. Stuff like data structures and algorithms, but also access to file systems, memory management, process management, networking. Almost every programmer of traditional applications operate at this level. So compared to the freestanding world, in the hosted world, you feel like a superhero. But the problem is that much of this added functionality depends on an underlying operating system. And even though you are isolated from directly dealing with one, the programming language runtime has to deal with one. And now here is an unspoken secret when you hear news that a given blockchain project now supports a given programming language. What they mean is that they support something like a freestanding implementation. But it just doesn't cut it, right? I once had to implement a logarithm function because the language didn't support, or the implementation of the language didn't support. Some people like this kind of challenge. I, in fact, do, right? But I also have deadlines to meet, right? I have two young kids, I have other stuff to do. So we want to support as many hosted programming languages as possible. And the way to meet all the resulting dependencies is to actually run an operating system. And then Linux comes to mind right away. So an OS controls access to all the resources in a computer. For example, the memory used by each program's time in the processor, whatever devices you have plugged in. And this in fact allows different software components to collaborate without getting in each other's way. The OS also provides a bunch of facilities most software has come to rely on. For example, memory management, process and thread management, different file systems, networking. Nobody should have to re-implement this stuff. We just want to use it, right? We've grown used to it. The OS also isolates programs from details of different devices that might be connected to a computer. It hides those behind drivers and then offer a uniform interface that programmers can use. This is less important to us because we don't intend to hook up different webcams to the blockchain, right? But it's still good to have. The thing is that operating systems also have needs. They co-evolve with the underlying hardware on which they run, and they now rely on a bunch of hardware features to work properly. For example, OS code can do stuff that user programs shouldn't be allowed to do. The memory used by the OS is protected from access by user programs. In fact, even memory used by user programs is protected from other programs. So to prevent one program from hogging the processor, the OS can unilaterally regain control of the processor. These things require the architecture to support features such as privilege levels, memory protection, virtual memory, timer interrupts, and a bunch of other things. Not all computing architectures satisfy these needs, right? Notably, WebAssembly and the EVM, and pretty much every other blockchain-related VM out there do not support these things. And they were designed to run over an OS, not under an OS, right? They were designed with freestanding implementations in mind. In contrast, pretty much every modern hardware instruction set architecture satisfies these needs, right? They are pretty complicated beasts. I guess you could create your own, but you probably do a lousy job at it unless you are one of the few specialists in this field. So it's actually better to pick an existing one and focus on desired properties. So you want an open standard, you want a smallish specification, you want good software support, like you want this thing to already have Linux support, have compilers for it, and all these goodies, right? Otherwise, you'd have to create them from scratch. And the choice that comes to mind is RISC-V. Recall that programming language standards, at least the C and C++ ones and some others, were divided into two parts, the freestanding part and the hosted part. And the same thing happens with RISC-V specification and other hardware architecture specifications. They're divided into two parts. There's the unprivileged specification, which is basically what a compiler backend for freestanding implementations of programming languages would need, right? But then there's the privileged specification, which is in addition, all that an operating system needs, and then indirectly what you would need for a hosted programming language implementation. So the parts of the RISC-V specification, these two parts are divided further into extensions, and different implementations of the architecture can pick and choose which parts and which extensions they want to offer. So for example, 64-bit support, integer multiplication and division, atomic operations, floating point, compressed instructions. These are all separate extensions in the non-privileged part of the standard. Now, the privileged part mandates at least a machine instruction set architecture, but it leaves supervisor and virtual memory as optional. Linux distribution have adopted the blue ones shown here as a working minimum. And here's another secret. So when you hear that a blockchain project supports RISC-V, what they mean is they support the non-privileged part of the standard and a small subset at that. So they can't really run Linux directly. They can't even run the Linux kernel directly, much less a Linux distribution. So the Cartesi machine is our RISC-V architecture and emulator, right? It's complete enough to run existing Linux distributions unmodified. We support all common extensions, including floating point and even the hypervisor extension. So all you need is a very simple patch to the OpenSBI firmware, and we need one kernel module that supports rollup input and output, right? We have a driver for that, if you will. This architecture and the emulator itself were designed specifically to support dispute resolution, right? So the emulator can be embedded inside other programs. It has an extensive API and binds to a variety of programming languages, so you can control the emulator inside your own program. And of course, you can run, the applications will run inside the emulator, but the emulator itself can be controlled by a node, if you will, that is running the computation. And it can be stopped and restarted from any instruction cycle. And at these points, it can also be saved to disk and loaded back. It obviously runs are reproducible, right? This is something that every decentralized project needs. It doesn't matter in which computer you run the emulator or how many times you run a given computation, the results are always the same. This obviously implies that the emulator can be run in a self-contained mode, right? So nothing in the outside will affect the result of the computation. But more importantly, the emulator is fully transparent. So you can inspect the entirety of its state from the outside, and the emulator can even log what access to the state happened over the execution of each instruction cycle. The entire state of this emulator is mapped to the RISC-V 64-bit physical memory address space itself. This is a trick we use to be able to identify each piece of the state in a uniform way. In practice, obviously, this address space is sparsely occupied, right? It's large address space, not as large as the EVMs, right? But it's still pretty large. So it's divided into a bunch of linear memory ranges. And the most obvious memory ranges would be the RAM, right? The memory, but also flash drives, say, containing a root file system with, say, some version of the Debian Linux distribution and your application program inside, your DApp inside. There's also a special memory range that is used to receive rollup inputs and to send rollup outputs. So this is what will be controlled by that Linux driver that I mentioned. And there's another one that you can reserve to put your application state. So this would be like the exchange, the wallets of all users and the orders that are pending in the other books and stuff like that, right? But crucially, there is a shadow memory range that contains all the general purpose registers, the floating point registers, the program and cycle counters, and many other control and status registers, right? So this memory range here. And this is all the stuff that the emulator needs to do its emulating. So the address space is then divided into 64-bit words, and this array of words is then Merkleized. Now, obviously, this will end up being a very sparse Merkle tree, but it locks the entire of the state into a single state hash. So going back to disputes, we had narrowed down the disputes to a single application of the transition function, big F, over M sub I, and the honest party must now prove their opinions. But F is just some software. In our example, it was an exchange, and M is just some data, right? The balances and open orders in the exchange book. So we wanted to transplant this software to a special machine so we can continue dispute of chain. And of course, we will move this to a Cartesi machine. We do this through a template, and a template is just a snapshot of a machine that was agreed upon to settle disputes over a certain application. So to create a template, you start from the machine, from a machine that is ready to boot. We put Linux and the firmware in the machine RAM. We set up the program counter to point to the RAM. We then plug in a root file system with a Debian and your DApp binary and all its dependencies. And we set the init script to run the DApp, right? We then run this machine. And what will happen is that it will boot Linux. Linux will run init will run the DApp. And then the DApp will ask for the next input from the driver. And a template is a machine that is stored at exactly this stage. Yeah, in other words, it's missing the next input and the DApp state, but it already embodies the application transition function, the big F function. So base layer knows the hash of this template, the Merkle hash of the state of the machine that is this template, right? We don't care about most of the state. For example, the shadow and the RAM you don't want to look into them, right? They are not easily understandable. They basically contain a booted Linux OS with a program in mid-flight, but it's basically F. It's an embodiment of F, right? The thing is that base layer can then splice the M sub I into the template. To do this, all it needs is a few hash operations, right? And it can find the hash of the machine with the rollup input and the DApp state, the application state already patched into their memory ranges like this, right? It's a typical Merkle tree operation to do that. Now, the Cartesi machine has a transition function that is simpler than the transition function of the application, right? It's at least less expensive to run. It's just a single instruction cycle from the emulator, right? So what we do is we run the machine for as many cycles as it takes to reach a fixed point. In practice, this fixed point will happen when the application invokes the driver to say that it's done with the input. And at this point, the application state, the modified application state, and the outputs it generated will each be in their designated memory ranges, like here, right? And if you know the hash of the machine at this stage, right, you can then slice out these ranges to recover the results of applying the big F over M sub I, right? You can recover M sub I plus 1. Now, obviously, the two parties in the dispute will not agree on this fixed point, right? And so they will disagree somewhere in the sequence. And we just keep doing what we were doing, right? But now we're doing it instruction by instruction in the Cartesi machine. We asked if they disagree before the midpoint. And if by doing this, we can halve the interval of disagreement, and we keep at this until we reach a single Cartesi machine instruction. And now the honest party must prove their opinion about this transition. But then how, right? So the problem is that this transition function is too complicated for base layer to implement. We needed a bunch of extensions to make the machine useful, right? So floating point, also a TLB for virtual memory, like these things are complicated, but without them, we wouldn't be able to boot Linux, or we wouldn't be able to use a standard Linux distribution, or it would be inconvenient to do so, right? So this would prevent developers from migrating their codes to run inside a Cartesi machine in the first place. But now imagine having to implement, say, floating point to run on base layer, right? And not only that, but an implementation that actually matches the one off-chain. It would be kind of a pain and maybe insane. So that's not what we do. We instead define a microarchitecture. Now, this has an even simpler transition function, right? It's only the non-privileged part of RISC-V, so no extensions, just the bare minimum to execute the big architecture, right? So the big architecture that we described with all these extensions. So the microarchitecture state is also mapped to the same address space as the rest of the machine, but it has its own shadow with its own tiny registers and flags. It has its own small RAM. So what we do is we compile the transition function of the big machine to run on this much smaller machine. And in fact, the compiled big machine already comes preloaded in the template itself, right, in the microarchitecture RAM. So we can run the big machine directly on the host, instruction by instruction, or we can run each of these instructions as microcode running inside the machine, is the small machine, right, the microarchitecture, micro operation by micro operation. So this is the point at which our interests start getting nosebleeds because we are too deep in the recursion, right? It's like that movie Inception. So a dream inside of a dream inside of a dream, right? So let us recap. We started with an application running bare metal in the host computer at full speed. Somebody disagreed on the results, and we managed to narrow down the disagreement to the processing of a single rollup input, right? We then moved to running a single input inside the Cartesi machine. This is our emulator, and the emulator is running bare metal in the host computer, but the program is running inside the emulator. So the two parties will obviously disagree on the result of that as well. And so we can narrow down their disagreement to a single instruction of the big emulator of the Cartesi machine. We then moved to running that single big instruction inside the microarchitecture. And we can now narrow down the disagreement to a single micro operation. Now, this micro operation we can prove to base layer. And to prove the transition function, we have two mirror implementations of this transition function. These implementations use basically the same source code. The trick is that the off-chain implementation can collect the log of all the accesses that it performs to the state, both reads and writes, while executing a micro operation, right? So something like a word was read from a given address with a certain value, And here's a proof based on what we know to be the current state hash, like a Merkle proof. Or maybe a word was written to another address with a value that we know. Here's a proof that lets you figure out what the new state hash should be. So we pass this log to the base layer implementation, and it will execute exactly the same logic as the off-chain implementation. But when it tries to read or write to the state, it consumes and verifies one entry in this log. And but only the honest party can provide a log that starts from the correct state hash and is then accepted by base layers. Now, there are other possible designs, potential designs, right? For example, maybe you don't want to write your application code very carefully so that you can run it in bare metal, right? After all, you have to make sure it is reproducible and self-contained. And so you wouldn't be able to use a native floating point, and otherwise you might end up obtaining different results in different architectures. You could just run it inside a Cartesi machine directly, right? There'll be an overhead, of course, but it will automatically be reproducible and self-contained, no matter what you do. Like, no matter if you use threads, it really doesn't matter. Or maybe you want to reduce the number of stages in this dispute that I described. So for example, you could use ZK to prove a bunch of state transitions directly, right? And we have a prototype in which one of our people compiled our program, our big emulator, right, code to run on RISC-V, right? So in a sense, RISC-V can run our microcode. Or maybe you want a different OS, right? Just check if it has a RISC-V port. A bunch of them do, right? So Nix OS, SEL4, which is a formally proved operating system, kind of a microkernel. There's a bunch of others there. So it should be possible to use those instead of using Linux. If there's some interest, let us know. Or maybe you want to use a different sequencer for your rollups, say, I don't know, Espresso or something like that. And we have kind of a prototype that allows generic I/O to get inputs from other sequencers. So the point here is that we are modular, we're open, and so you can just take bits of our stack and have fun and let us know about it in our Discord channel. Now, what is this all good for? If you go to rolluplab.io, you will see a bunch of ongoing projects from the community. So these are all full-blown applications, right? They include interactions with base layer and front end, in addition to the backend that runs inside the Cartesi machines. Now, in the past, we've had a lot of trouble explaining to people why these count as decentralized blockchain projects, right? Because they see Linux and they think we're crazy. And then it clicks, right? And indeed, some of these projects have now been finalists in Ethereum events. I'll only mention some, like a couple of these projects. Please go look up the author presentations. They do a much better job explaining their vision than I ever could. So for example, there is this decentralized bug bounty program called Bugless. And the idea is that you put the software that you want tested inside of a container or perhaps a hypervisor guest OS inside a Cartesi machine. Now you can pass inputs to it. And if somebody manages to crash the software inside a Cartesi machine, then the Cartesi machine will issue a voucher that will allow the person to cash out the price. There is no middleman here, right? People can be sure that they will get their price. So here you see the UI where they tested a known exploit to a certain version of Lua just for fun. The prototype supports a bunch of programming languages and software packages. And I think this project has a lot of potential, right? They are currently adapting this to allow for bounties on EVM smart contracts, for example. If they use our hypervisor extension, then they could even test the Linux kernel itself, or they could use this to test Linux system tools, right? In a decentralized way. So Cryptopolis was, in fact, an ETH Online 2023 finalist, right? So top 10-ish from around 500-ish projects. it was a one-man project, right? So Danilo, our Danilo took the C++ port of the original 1989 SimCity code and compiled it unmodified to run inside our emulator. He then added a Node.js binding to control the game programmatically. And he came up with a pretty nice way to tie up the game economics to use tokens, right? So it became an actual economy. The whole thing runs as a rollup. Think about the freedom that he had to use the tools that he wanted to compile this project, right? He used different tools than the tools I would use, right? He's very familiar with Node.js and bindings and C++. Maybe I would use Lua instead of Node.js. But I mean, it's the thing that he's most familiar with. It's a lot of freedom, and that's what we are all about. So now I'll change to the final part of the talk, in which I'll go and talk about playing with the emulator itself, right? I'm not going to talk about messing with interactions with the blockchain or talking about front ends. I'm an emulator guy. I'm going to mess with the emulator and show what it feels like to do that. Peter, I don't know if you want to open for questions before I transition to the demo, and then we can do more questions.
Yeah, I think that's actually a really good idea. And I know one of the questions was, is there a demo or is it just theory? So we've already got the answer for that one.
Yeah.
Beyond that one, does anyone have any questions? So I do. So, we've seen a little taste of things already, but so is the idea, say that SimCity rollup as an example. So you would play SimCity and what the rollup would prove that SimCity executed correctly is
So you would in that particular game, you would have a wallet with a certain number of tokens that represent the money that you have. I don't know if you've played SimCity, right? So there's an economy. You need money to buy things and make things happen. And so on Ethereum, you would have deposits happening periodically like you have in the game, right? And then you would send a command to the game to the sequencer saying, I want to build a building here in this position, and I want to do this other thing here, construct roads and a factory and wiring and all the stuff that you do in SimCity. It would grow as inputs to the rollup, and then the Cartesi machine with the SimCity code inside would take inputs from the rollup and apply them to the game and evolve the state of the game and produce more money. If there's more money to be produced, this would be feedback. And so it would be possible for you to prove that, here's a set of inputs that I sent that created this thriving city, this thriving economy. And then you could use that in competitions. You could maybe trade tokens between different cities. It's a big space, right, of what you could do. But this is all possible because, the game logic is provable, right? It's running inside a thing that is provable.
Yeah.
Does that make sense?
Yeah. So it sounds like you could do quite complicated multiplayer on-chain games.
Interactions. Yeah.
Well, it's generally, like you want to keep your game logic off-chain and just do critical things on-chain. All right, that's very interesting. Does anyone else have any questions?
Don't be shy.
No,
yeah.
I think,
I've got a question.
Go ahead.
Yeah, of course.
You talked about using other operating systems that run on RISC-V. So, for example, you gave the example of FreeRTOS.
Yeah.
Right. So, we're talking about an emulated environment, within the system. Would you be able to use a device on the edge that runs RTOS that would look like it was inside the rollup and use it as it collects data and use it as part of that whole environment in whatever solution you might build?
So what you're describing is a problem that is every blockchain has, right? Which is, how can you bring data from the outside world? Like, people used to call this a type of oracle, right? So whatever data you want to feed inside, the machine has to be provable to base layer. And so to the extent that these devices post signed inputs somewhere to base layer or to the sequencer themselves, we could make it look as though the actual devices are operating inside of a Cartesi machine, right? But then there's this problem of making sure the data that appears there is known, at least provable on base layer, right? Otherwise, it has to be self-contained. And in a sense, those inputs in the sequencer are a solution for this, right? So you can imagine that you have devices that are posting signed data to the sequencer that is used by the Cartesi machine, and then we can make those appear from inside, say, Linux or RTOS or whatever is the OS.
Okay, cool. Thanks.
Yeah, I think that's it. So let's get on. Please do your demo.
Yeah. So let me see how I do this. Wish me luck. So here's an example of how you can make a root file system, right? For to run inside the Cartesi machine. So we actually use Docker for this. Can you imagine? So we say here, I want to produce a file system that is based on RISC-V, right? And here's the base image. And we just copy some of our tools inside. We have a Debian package for it. And then we just run regular Docker things, right? To produce an image. So we're installing BusyBox, which is kind of an embedded version of a bunch of system utilities to make the image small, core utilities, bash, right? Our tools. Then we create a user home directory, and that's it, right? And I already built this, right? So there's a command line that I can run to do this. For example, build. Let me show you the build script. Right, so this is a build script that I created. It uses Docker to build a tar file with the file system, and then it does some things just to ensure reproducibility and generates an ext2 file system from the tar file. That's all it does, right? So I could run it, hopefully. So Docker file, basic, 128 megs to a.ext2. It's running Docker. And there you go, right? It's an ext2 file system. So I could run our emulator. Let me just clear this here. I could actually run our emulator, right? And here's the command line, right? So this is, I'm using our Linux kernel already linked with the firmware. And I'm saying, for the flash drive root, use this rootfs file here, which is a file system, and be quiet about it. And so it just printed a splash screen and said, you didn't ask me to do anything. But doing anything actually means doing a lot of things, right? Because if I ask it to be verbose, you can see that this thing actually booted Linux, right? So there it is, right? The messages that Linux prints while booting, and then it ran our init script, right? And init script printed the splash, and then said, I have nothing to do, and then it powered down. That's what it is. Now I can do the same thing, but now I'm going to ask the machine to show me the state hash at certain points, the state hash of the machine, right? So here's what it did. So this is the Merkle root of the entire machine state before it executed the first instruction cycle, right? And here is the state hash when it was done processing, right? When it was halted, in a sense, at this instruction cycle. So this thing ran, I don't know, 36 million instructions to do nothing, right? Now I'll show you something a bit more interesting, which is I'm going to stop the machine in the middle of the splash screen, right? Save it to disk and ask it to compute the hash when it started and when it saved it to disk. And then I'm going to load the machine from disk and print the hash that it has at that point, and then let it go until the end, right? So here is the, oh, hold on. So check this out. So this is me asking the machine to stop at this big instruction cycle with a certain number, right? But also print the initial hash and the final hash, but store the machine once it stops, store in this directly mid-splash, right? And then run again the emulator, loading from mid-splash, and also printing the initial and final hash. And you see the initial hash that he printed here was the same as the initial hash that it had printed before, of course, right? And then this is the hash at the midpoint, right? And then the machine exited and it started again printing the hash in the beginning. It matches, which is reassuring. And then it goes on printing the rest of the thing and saying nothing to do. And here's the final hash, which again matches the final hash that it had if it ran directly. Does this make sense?
Yes, it does to me. Yeah.
Yeah,
Awesome.
cool.
So now I'm going to do something a bit more insane, which is I'm going to pretend that, so let me run it, and then I'm going to explain what it's doing. So I'm going to pretend that we already had a dispute. We're in the middle of a dispute. We narrowed down a certain input for rollup, right? And then we said, oh, actually, the big instruction cycle that we care about is the cycle 1000. And then we moved to the microarchitecture and we kept doing the search and I figured out, oh, actually the instruction cycle, the micro instruction cycle that I care about is this one, right? So this is like little f, little m sub 1000, right? And this is phi and mu sub 6402. And then I told the machine, you know, run until exactly that point, first running the big instruction cycles on the host, and then switch to the micro instructions and run 6,402 of them. And when you're done, print the log of the next instruction. And here's, of course, this is human readable for a very special kind of human, right? But it is a visualization of what the state transition log would look like. And what it's doing here in the log, you will see that it's reading the cycle counter, right? And it found the value that we expected there. And then it read the halt flag to see if it should be halted already. The micro architecture should be halted. And it found that it's a 0, so it's not halted. So it goes on and he reads the micro instruction program counter, right? And the value that he finds there is this value here. And so he goes to memory at that address and reads the instruction itself, right? Now, the instruction happens to be a store double word, a RISC-V store double word instruction. And to execute this instruction, first you read the target address for the store, and this is the value, right? And you also read the value that you want to store. You want to store 1. You will notice that this address is exactly the address of the halt flag here, right? So it's writing halt there. It's writing that the thing is now halted. And so basically this is the write to the state saying that the microarchitecture is now halted. And then it advances PC, right? To a new value, adding 4. And finally updates the cycle counter to the next cycle counter. Now this is, I picked this number because this is exactly the halt the microarchitecture, right? And I knew that I would be able to explain what's going on this one. Does that make sense again? So each of these operations will be backed by a Merkle proof that on reads prove that the value read at this address is what it is, and on writes allow the base layer to produce the new state hash once this this operation has been performed. Does it make sense?
Yep, sounds cool.
Now
Yeah.
let's stop. Yeah, go ahead.
No, that makes sense. Yeah.
Okay. So let's ask the machine to do something. So here we're passing it to run echo hello world, right? This is actually running inside of bash. Just think about it for a second, right? It's just printing hello world, but behind it, there's a lot going on, right? Now, let's have some fun here. I'll show you a different Docker file. And this Docker file includes more stuff. It includes our tools, right? But also a device tree compiler, JQ, which is a way to mess with JSON files, the calculator, right? Curl to get data, Lua and a few modules, XXD to inspect files, wget. I don't know why I have wget and curl, but just pick whatever you want. VI. I'm a VI guy, sorry, Emacs people, and a few other things, right? And I already, and then copy some Lua files inside the, create a user, right, dap, and copy some Lua files in there. I already have this, rollup, this root file system built here, right? So I'm just gonna go and run it to show you. So, and there you go. So now instead of using bash, I'm using Lua, right? And printing hello world. But I could show you something else, which is this, right? So this is another Docker file. Now this one is based on just like people that use Docker do, right? So I'm just using a different base image here. Here's one that includes Node.js. I'm not a Node guy, but Danilo is, right? You might be. And I'm just taking that base image and installing our tools. And I can now, I already have this, this root file system built here. So I can actually run it. Thing is that Node takes some time just to initialize, right? But still acceptable, right? This initialization would already be in the template, so you wouldn't pay for the initialization itself, right? But still, it's pretty decent. And now I printed hello world using Node. The thing is, just do whatever you want. Pick whatever tool you want to get the job done, right? Now, obviously, when you are prototyping, you can run the emulator in an interactive mode. And this will not be reproducible, of course, but allows you to have a lot of fun, right? So here I'm inside the emulator. And I shared, so what I did was, I said, share the current directory and mount it at MNT here. Add network support, make it interactive with enhanced terminal. So this is the listings, right, that we had outside. It's showing what's in the outside world, right? But you can also do curl. You have network support. This is what this is what Google uses as an index.html. And you can even VI. You could change this. You could do whatever you want, right? It's prototyping. And you can also run in interactive mode. And you can actually compile this emulator to run inside of a browser. And we have some crazy people that did that in the foundation. And so I don't know, I'm gonna suck at this. So I don't even know what the keyboards are anymore. I don't know how do I shoot? Oh, okay, at least I can shoot. So this is running Doom. Some violence here. Anyway, so this is just running it inside the browser in an interactive mode, right? And one application for this technology is you could collect the log of all the keystrokes that were generated and the times at which you fed them to the emulator, and then you can use this as a rollup input and verify a high score for a game, for example. Does that make sense?
Yeah,
We have.
assuming that
Go ahead.
the game's deterministic, I guess it does.
It is, because it's inside the Cartesi machine, right? The
Yeah.
only thing that would not be deterministic is the user input. But if you collect the log at exactly the instruction cycles at which you're feeding those to the machine, the whole process becomes deterministic.
Yeah, that makes sense. Yeah.
So let's now create one of those templates, right, that I talked about. So first, let me show you a shell here script. This is a shell script that I'm going to run inside the Cartesi machine, right? And it's using our utility rollup saying, all right, give me the next input. And I'm just piping it to JQ so that it pretty prints. This utility returns the next rollup input as a JSON file so that you can mess with it. And here I'm just printing it just to show you guys, right? And so the command that I'm going to run is this here. And here's what we did, right? So we copied the script itself directly to the init file that we have inside. And then we've asked it to store a template, and I asked it to give me the hash, right, of the template. So this is what base layer wouldn't be aware of. It would be aware of this hash of the template, right? But now what I'm going to do is I have some rollup inputs that I'm going to feed directly to the machine, right? Because I'm a machine guy. I like to be able to do everything without connecting to the outside world. So I created some rollup inputs that I'm going to feed directly to this thing. And so here's the command. Let me show you. And it's doing its thing. So let me show you first the command here. So this is where it begins, right? So it loaded the template, right? And here's the hash of the template. And then it patched together the input, and it might have patched the state as well. But here we don't have a state to carry over, but it patched the input. So it changed the state hash, of course, right? So base layer will be able to obtain this hash, and this is the hash of the machine that it's supposed to run to do disputes over that input index, right? And so it runs the program inside, and JQ just prints the JSON that rollup command generated. And you see, this is the payload. This is input 0. At that point, the machine has this state, right? And it patches the new input. So it changes the state, and here's the new input. And then at this point, the machine has the state, it patches the new input, it has the state, and so on. This is sort of what would happen during a dispute. Does this make sense? Just showing the inputs from the inside. Yeah? Okay.
Yeah.
Now, we're not doing anything with this, right? So let's show a different script, right? Now this script is using the same rollup accept, but it's selecting just the payload, right, inside this variable, and then it prints the variable, but it also passes the same thing to the application, the calculator application, right? So I'm now going to run this on a few expressions, right, as though the inputs contain the expressions. And so you will see that I'm using a different set of inputs here than I was using before. But here's what this looks like. So the input was 2 to the 2000, and this is what BC produced, right? Then 2 to 200 and 2 to 20, right? Just performing some computation, you can imagine that, you know, if people really care about the value of this computation, and instead of just printing it, we would actually output a notice that is provable to base layer, or even a voucher. You know, you can do whatever you want, right? But this is just showing how it's easy to just do simple computations. Now I'm going to go one step further and show you another advantage of using a full operating system, which is, let me show you this. This is a Lua application, right? And the Lua application just loaded a package for JSON manipulation. It then loaded a very simple library to deal with rollup inputs, got an environment variable, the address, to figure out what the address is of a HTTP server that we're going to run inside. And now applications will use that HTTP server to get the inputs instead of using that rollup utility, command line utility, and instead of talking to the driver directly. You just use an HTTP server. I'll show you in the command line how this works. But what it's doing is just using an HTTP post to that URL saying accept, and this means give me the next input. Then it takes the response, which is going to be a Lua table representation of that JSON, and just removes X encoding, because the server uses X encoding, right? Because the payloads could be binary. And then it just encodes that into a string without the X encoding, right? So it's a very simple program. But to run it, what I'll do is this here. Let me show you. Okay, so let me show you the command itself. I'm saying, okay, append to the init script the address of the server. Then run our server. The server is the one that is going to get inputs from the device driver and pass it down to whoever requests them using HTTP, right? It's almost like a bridge between having to deal with devices to dealing with HTTP, which is something that most programming languages can do. And so it allows us to not to have to implement bindings to our driver to every programming language out there, right? And the server will be listening at this address. And then I'm going to run Lua and run our DAP there. And what is happening is you're going to see some diagnostics from the HTTP server itself. It's saying, sure, I'm running the Lua script that you asked me for. And, oh, wait, I received a post to the finish entry point. And then the Lua program is now outputting this, right? It's that JSON, right? And the payload this is input 0. And then it does the same. The server reports that he received another request, and Lua prints the next request. This is input 1, and so on and so forth. Right? Does this make sense? I could have used Node.js to do that. I could have used Python, and people have done that, right? Are you guys still with me on this?
Yeah, we've got a thumbs up from Mark, and I'm still here. And yeah,
Nice.
I'm watching and yep, absorbing.
Yeah, it's a lot. And now I'm going to do something very, very crazy, which is I am going to show a prototype of that exchange example that I mentioned. And to do that, let me show you. So this is the directory of the exchange the prototype that I wrote with the help of a friend. And, you know, it has a CPP here that is just a C++ code. Some includes, you know, like this is a JSON library, and that's it, right? But I will show you a Docker file that I used to build this to run on the host. So I'm going to run this bare metal in the machine, right? But I want to run it on Linux, so I'm going to run it inside Docker, right? Because I'm on a Mac. And so this is a Docker file for the host. And what it does, it creates a multi-stage, it's a multi-stage Docker. So it creates an image that is just to build the application, install GCC 12 inside it, right? And then it copies the Lambda-X source code there and makes a host executable, right? And then it creates an image that is the one we'll actually use. And it just copies the compiled host to /home/dep, right? So I'm gonna now run this, the resulting Docker file. I mean, I could build the Docker file. Let me see if this works. Yeah, so I'm going to now run the exchange, and the command line is gonna be a bit crazy, but I'll explain it here. Okay. So here's the command line that I ran, right? So I said, okay, run this application here from the image Lambda-X, right? Share the current directory in a shared mount point and move the working directory there. Make it the working directory, right? And now when I run this application, it's gonna use an image file name that I'm calling Lambda, just like Amazon Lambda, right? This is the state of the application. You will notice that first I am erasing it if it exists, and then I'm creating it anew with zeros. So this is the initial state of the dApp, right? And it starts zeroed. But when I run this application, I'm asking it to initialize its Lambda state, right? And I'm saying, you know what, pick inputs from these files here. I created inputs to the exchange already, right? And metadata for these inputs. And I'm saying, you know, feed inputs from 0 to 5 to this. And then it starts running and the dApp is reporting, okay, here's the virtual start. This is something that I'm going to explain later on. But it's basically saying, okay, here's the first input. It's an ERC20 deposit, successful deposit with this token to this trader, right? This is the sender will be a trader. And here's the amount. So this is something that would be received, an input that would be received from an ERC20 portal to the sequencer. And it would only be issued if the same token amount had been already deposited to the exchange wallet in base layer. And now you're just telling the application that, you know, this deposit has happened. And then it just publishes a notice, which is a verifiable output from the machine saying, you know, trader such and such now has this token, this amount added to the deposit. There's another deposit for a different token, right? One of them is CTSI, the other one is USDT. I didn't have time to put the translation here. This is the sender, here's the amount, and it outputs the notice. And then it receives another input, which is actually a new order. So this is a buy order from, and it will have been received from a contract owned by this trader here, right? So this is a trade order of buy 1,000 CTSI at 15 cents per USDT, which is a pretty good deal at this point. And then a new order arrives. This is from a different trader. This is actually a sell order, right, for a certain amount. And then it's outputting notices that it closed some trades, right? It closed a few of these trades. And then a new order arrives, and then it closes again, right? And then there's a withdrawal, right? And the withdrawal generates a voucher, which is this transfer that the whoever asks for withdrawal, there's a logic inside this code that will check if they have enough money inside the wallet. And if it is, if they have, it would issue a withdrawal, right? And then there's a notice. So basically, this is like the simple workings of what an exchange would look like. Does that make sense? Now, what I'm going to do now is I'm going to take the exact same source code. I'm going to change the library that it uses to get inputs. Rather than getting inputs from files, you will now get inputs directly from the Linux driver, and I'm going to compile it to run inside the emulator, right? So if you look at this here, I'm using now a cross-compiler builder. I could actually build it inside the RISC-V emulator directly, but I prefer cross-compiling because it's faster. So I set up a cross builder here. I added basically our Linux kernel headers, but also the cross-compilers to RISC-V, GCC 12 again. Added the user, copy lambda-dex there, asked it to build the binary, and then I created an image now that is a RISC-V image, and just the regular stuff that I did, that I usually do. Just now I actually copy the emulator version of that exchange to the DApp folder, right? And I already built this here. Let me just run it. And here, check what I'm doing, right? So I created the lambda state. I killed it, right? Created an empty one with zeros. This is a different file than the other file, just because I want to have both files available. And then I'm running the Cartesi machine, right? And I'm passing this command line here, asking it to initialize the lambda. And what is cool is this line here. I want you guys to take a look at this line here. What I'm saying is, add another flash drive, but this flash drive, I want to use the label lambda, and I want to have it associated with this image file name, which is the lambda state for the exchange, right? Which is the state of the exchange. I don't want it to mount because it's going to be a raw file system, a raw flash drive, a raw device, but I want it to be shared. And what shared means is that changes that happen from inside the emulator to this flash drive will actually be reflected in the image file on the outside of the emulator, right? If you don't put shared here, then everything happens as a copy on write, and no changes are made to, say, the root file system. If somebody changes the root file system inside the emulator, those changes are not reflected. But on this thing here, on this file, on this drive, the changes will be reflected on the backing file. And then I tell it to run the same inputs that I ran the exchange bare metal, but run it inside the Cartesi machine. And it goes and it produces the same messages, right? And if we look here, let me see if this is true. What do you know? The hashes of the state of the exchange are exactly the same, running inside and running outside. Now, this is kind of baffling if you think about it. And we created this tech demo just to shock people in our group, right? So this state is actually contained in a bunch of C++ containers. So multi-maps, unordered maps, STD arrays, they're the native containers, right? And the same containers are being used inside and outside in a way that makes the state match bit by bit, right? And in fact, I can then inspect the state from the outside to see what's inside it, right? So instead of running changes to the state, I can do, what's going on here? Yeah. So I now just ran the program on the host using that Docker container that I had, right? And I said, okay, here are a few queries that I had produced already. And I said, I know that the files are the same, right? But just to make a point here, I'm using the state that was produced from inside the emulator, but I'm running this outside the emulator to inspect the state. And there's a query there for the wallet of trader such and such. And there's a report generated that says, oh, this wallet has 2 entries, and one entry is this token here, and the quantity is, I don't know, 97,500. And there's another token, and the quantity is 70, right? And then there's another query, which is like a book query. And says, so give me the trading book, the order book for CTSI and USDT at a depth of 10. And then the report says, oh, here are the orders, right? There's a book entry. There's an outstanding buy order of 500 from this trader. And then there's an outstanding sell order for this quantity by this other trader. And you can imagine that if you're working on a back end, on a front end, you would then use something like this to get all the data from the exchange and put it on some UI and populate it somewhere, And yeah, that's all I got for today. And let me know if you guys have any doubt. And if you have any questions, hit me.
Well, go ahead, Mark.
I was just going to say that was very interesting, Diego. It's kind of going to take a bit for me to digest and think through, but yeah, it's quite fascinating. Thank you.
Yeah, you're welcome.
So in one of the a few slides ago, there were multiple trades that were happening. Someone was transferring and someone was doing this, someone was doing that. Were each of those line items separate transactions, or was the overall a transaction that then could be proved? So it was.
So yeah, so there are 2 different ways of doing this. In the world of rollups, right? Usually you use what is called a sequencer. And this is a way for people to bundle a bunch of different transactions inside of a single base layer transaction and aggregate them together, right? Some people used to call them aggregators, but now they're called sequencers. But the idea is that you can aggregate a bunch of transactions in a single input, and then you could have code inside the exchange and the Cartesi machine that go over an aggregate inputs that has already been ordered by the sequencer, which is why it's called a sequencer now, and then verify each one and process each one of them. So it could be a single transaction that contains multiple, say, deposit, withdrawal, trade orders, in a single one. But here, for simplicity here, I did each one as an individual transaction just because it's more convenient. But you also, because of fear of censorship in sequencers, you always also have a way of going straight to base layer and saying, no, here's my order. I don't trust this sequencer anymore. I want to actually go to base layer and put an order. And so that would be like a single order that would appear as a non-aggregated input.
Okay. All right. That makes a lot of sense.
Now, it would need to still verify the signatures, right? If you do aggregate orders, you need to verify signatures, and there are aggregate methods of verifying signatures of the whole thing very easily. But I didn't do any of those things for this prototype.
Okay, fair enough. Fair enough. Are there any other questions for Diego?
None from me.
Okay, well, look, thank you for a really interesting talk, certainly a different way of thinking about things, I think. Certainly, yeah, makes us all think.
Yeah.
Yeah, which is good. Did you did you put those extra slides at the end?
Yeah.
Yeah, all right, good. Let's flip to them. So there's the store. Buy your t-shirts there. Anyway, next slide. All right. So we've got a whole lot of talks coming up. There are actually another two after this as well that have recently appeared. But yeah, so Frank is going to talk about his ideas of using a VRF, so verifiable random function in conjunction with the sequencer, so to allow you to have fair sequencing, so to prove that you're doing fair sequencing, which seems pretty interesting. Push protocol, it's like a messaging system. Sandra's going to talk about the EIP 7251. We've got another talk about the economics of ZK on Ethereum. So what makes sense, what doesn't make sense. I can't remember for the life of me what the next one is in early May, but then the mid-May one is the people from Layer 0 are going to do a super deep dive on V2. So yeah. All right, one more slide, please. Okay. If you're watching this here today live, please, watch it on YouTube or rewatch it, and we'll make the slides available on YouTube as well, in the description. If you want to discuss, join the Slack workspace. And if you want to join these talks live so you can ask tricky questions of the speakers, please feel free to, join up to the meetup and RSVP. It'd be great to have you along. So look, Diego, thank you very much for putting together such a great talk and live demos as well. That's, it always takes a lot of guts to do a demo. So thank you very much.
All right. Thank you, everyone. And we at Cartesi, we have a Discord, right? You just Google Cartesi and you will find our Discord, and you can go there. There is a machine channel where the low-level people like me live, and just ask away.
All right, that sounds awesome. All right, look, everyone have a great week or two, actually 3 weeks. So talk to everyone later. Bye-bye.
All right.
Yeah.
Take care.
Thank you very much for your talk. Bye-bye.